Hello, welcome to the Math and Physics Resource Center online from Saginaw Valley State University. My name is Amanda, and today we're going to be looking at Calculus 3, Math 261, using change of coordinates to integrate over a rectangular region. We're going to be looking at the example of sketching the given region and the new region in the UV plane, and we're also going to be solving for the integral. We're going to be solving for this double integral x, y, dA in the region R, where R is bounded by 0, 3, and x plus 3. And we're going to let x equal u and y equal v plus u. So let's start by drawing the region in the xy plane. So in the xy plane, it's going to go from 0 to 3 in the x. And in the y, it's going to go from y equals x. So that means it's going to go to 3 here. And it's going to go from It's going to start at 3, the next bound, and it's going to go up to 6. So now, here's our region. So let's mark the corners of this region. The corners of this region are 0, 0, 0, 3, 3, 6, and 3, 3. So now let's convert it to UV. So we know x equals u, and we can find that y equals v plus u. We're going to get y equals v plus x if we replace u and x, and we're going to end up with v equals y minus x. Now let's transform it. So 0, 0, u is going to be 0, and v is going to be 0 minus 0. U is 0, because u is x, and v is going to equal y minus x, so it's going to be 3 minus 0, so it's going to be 3. 3, 6, u is x, so u is 3, and v is going to be y minus x, so 6 minus 3, which is going to be 3. And 3, 3, y is going to equal x, which is 3, and b is going to be y minus x, so 3 minus 3, which is 0. So if we graph this new region in the UV plane, it's going to have the corners at 0, 0, 0, 3, 3, 0, and 3, 3. So the new region is going to be a nice little square. So now we can integrate. In order to work with this transformed integral, we need to transform our dA as well. We need the derivative of xy divided by the derivative of our uy. But the only way we can do that is by using the partial derivatives. So we're going to use the Jacobian matrix, and we're going to do the partial derivative of the function u in terms of x, and the partial derivative of the function u in terms of y. And then we're going to do the same for the v function. So as the Jacobian goes, you're going to multiply and multiply. So we're going to have the derivative of function u in terms of x times the derivative of the function y in terms of v, minus the derivative of the function x divided by the derivative of the function v in terms of x times the derivative of the function u in terms of y. So now let's find those. So we know that u equals x and v equals y minus x from our previous solvations. So the derivative of x in The derivative of the function u in terms of x is going to be 1. The derivative of the function v in terms of y is also going to be 1. The derivative of the function v in terms of x is going to be negative 1. And the derivative function u in terms of y is going to be 0. So it's going to come out to be 1. The new function is going to look like, well, for x, we're going to plug in u. For y, we're going to plug in v plus u. For dA, it's going to be our derivatives of x and y and v times our du dv, which in this case, our derivative of xy over our derivative of uv is 1, so it's going to be 1 times du dv. So our dA is going to be du dv. So now our du bounds, so in u, we're going from 0 to 3. And in dv, we're doing the same. We're going from 0 to 3 as well. So let's integrate. So 0 to 3 is 0 to 3. If you distribute, you get uv plus u squared, all that du dv. So if we integrate, in terms of u, we're going to get u squared v over 2 plus u cubed over 3. That's going to be from 0 to 3. And this comes out to be 9 over 2v plus 9. Now, last integral, we're going to be going from 0 to 3 for dv now. So now it's going to be 9 over 4v squared plus 9v, and that's going to go from 0 to 3. And that comes out to be our final answer, which is 47.25. Thank you for watching this video from the Math and Physics Resource Center from Saginaw Valley State University.